Oh, one last thing before I leave this topic. Notice the 45 degrees. Here we go. So the angle, the phase angle of this simple polar zero is given by the tangent, the inverse tangent of omega t, which is this red curve, this upper red curve that's labeled phi. Remember that the tangent and the sine, the derivative of the sine near 0 is equal to 1 if the angle is in radians, which gives us that 45 degrees per decade. So the asymptote, the inverse tangent, can be approximated by this dotted line for the phase. So this is kind of a complicated plot. Here's the phase, here's the magnitude. Moving on. Similar plots, simple zero. That a different zero now down here. So you have negative 20 dB per decade instead of positive. Okay? Not much to say about this. Just like before. Quadratics. So we take a look at this, and the phase angle is given by this. This is just some constant. It's the multiplier of the omega term, this theta here. It's a coefficient. Don't sweat it too much. It's just a coefficient. And the magnitude then would be 20 log base 10, and this would have to be the log 10 of the magnitude of all this stuff right here. The magnitude of it. So keep going. We do the same thing. We take a look at what happens when when you're at low frequencies, and then what happens at high frequencies, the high frequency asymptote. This 2 can get down there. This 2 right here will make a factor of 40, by the way. Note that. 40 dB per decade. Phase angle 180 instead of 90. When omega t equals 1, then we have a dB, and decibels are on a log scale, by the way. So it says the magnitude in decibels. You're taking the logarithm of the magnitude. When it's exactly equal to 1, that's where this constant comes in. This is a damping factor. Angle 90 degrees. Yeah, it's going to be pure imaginary. This is the only term that's going to have that's going to contribute to the quadratic, because this term equals this term when this is true. What they call the break frequency. Okay. And another condition now. So we have this this one right here. We plug this in there, up here, and we get this expression. This is basically constant. The angle at that point is going to be given by this, because you have the imaginary part. The real part becomes minus 2 zeta squared omega t tau squared over over the real part. Excuse me, here's the real part. Imaginary part, real part. So, and this is true, zeta has to be small enough. It can't be too big. If it's too big, then you have an imaginary value for the angle, which is unrealistic. It's a different solution when it gets to that point. It's a different functional form of the equation. This is at the resonance frequency, and it has to do with damping. So when there's zero damping, resonance frequency would be right at 1. Omega tau equals 1. But then as you have more and more damping, it kind of shifts the peak. There we go. It kind of shifts down like so. And that has to do with the fact it's friction. Damping is friction. Phase angles, phase shifts as a function. Okay. So this is for a pole, quadratic pole. If it's a 0, it's just flipped. Remember, a pole is in the denominator, a 0 is in the numerator. So these graphs here are reversed, flipped upside down if you have a 0 instead of a pole. Now, so we want to do this, generate the magnitude and phase plots for this gain. Break corners, let's see, this 0 would be a 10. I'll put a Z there for the 0. And it's the only 0 in the numerator. And this would be 1. And this would be, the other one would be 50. When omega equals 50. So we can identify where the, well, there's the constant gain, 10 dB. What 10 is in decibels. Remember, decibels go by power. So a factor of 10 in voltage is a factor of 20 in power. So that's the 10 factor, the constant. And we bring in the, let's see, that looks like the phase. Is that the phase? 0? Yeah. 0 phase. Now we go to this one. And it's a pole. And so it'll be, it's a first order, a simple 1. Okay, and then let's see, where's the break? This is the 1. Oh, excuse me. There we go. This is the one that breaks at 1. There, that's this one here. And the phase, 45 degrees per decade. And of course, these are approximates. The 0 on the top. So it does this. It'll go up at a high frequency. Break point was at 10. There we go. We're showing that. And the phase. Let's see. I'm looking at this and saying, does this make sense for this 0? That's right, it has to cross 0. So here's 0 degrees in phase, and here's the crossing point. Here's the knee. The knee is here. 45 degrees in phase is where the knee is. 45 degrees in phase is where the knee is. So this is the first one. This is this one. This knee here is for this one up here. And the last one is at 50. So there's the 45 until it before we get to the 50, we got to complete the phase for this one here, for the 10. Got to complete the phase for the 10. Okay, now the 50, the last term. So drawing a dotted line here, and it's a pole, so it'd be negative 20 dBs per decade. There's the dotted line, 45 degrees, phase angle of this guy is going down. So now we can draw the composite. That we have the unity gain, and then 0 gain, 0 dBs is multiplier of 1, by the way. Now next it's going to follow this curve. Because this is, when you add decibels, it's multiplying. So you're multiplying these factors together. This gain is all multiplied together. And this is a log-log scale. So now when this one starts tracking down, the composite can start tracking down. And you hit this point, now everything's starting to track up again. Here's the next point, next break point. This one's causing it to track up, but this one's causing it to track down, so that should be a flat line for a while. Yeah, flat line for a while. And now the last composite is going down. Okay, phases, very similar. So tracking down, and then this one's going up, but this one's still going down. So you flatline for a while. Then now this one's starting to go down. So you're going to go down for a while until you hit the 50. Until you hit the knee. Let's see, is that correct? Let's see what they're saying. So down, up and down, same amount, flat line. Oh yeah, you're starting to go down here. Starting to go down here. And yes, here's the next one. This flat lines. So you're starting to go down, and then you have a flat line here, which makes a composite a flat line. Boy, this takes some getting used to. Now the next point that changes, no change until you get to the next knee, in the phase diagram, that is. So you're going up and down the same amount for a while, so you're going to be flatlining, and then now you're just going to go down. You're going to follow the rest of it down. Everything's a flat line except this guy. You're going to finish off going down. And then finally, it winds up at its final resting point of negative 90 degrees. Okay, ending here. We will pick up the next one next time. Oh, might as well just, let's see, was this what we finally constructed? The composite? Yeah. The next chart is getting rid of all the drawing lines and putting in the composite stuff. Okay. Now, your turn.